Hi, in this video we're going to begin our discussion of the eigenvalue decomposition. By the end of this unit you should be able to understand and be able to define what is meant by an eigenvalue of a matrix, be able to solve for the eigenvalues of matrices that are 2 by 2, that are 3 by 3, or of certain easy to solve n by n forms. You should be able to do the same for eigenvectors and eigenspaces. Understand what they mean, be able to define them, be able to find a set of eigenvectors for a given eigenvalue. You should be able to put these ideas together to diagonalize a matrix and to use the results of the eigenvalue decomposition to solve problems. In this first video, we are going to give an introduction to the idea of eigenvalues, eigenvectors, and how we compute them. So far, our discussion in the class has really been focused on problems that can be expressed in the general form for a system of linear equations, A times x equals b, where A is a matrix of constants, x is our variable vector, and b is a constant vector. And problems involving industrial production and demand balance, industrial production resource balance, the Leontief economic equilibrium models, chemical equation balancing, all of these give rise to systems of equations that can be expressed in this form. Sometimes with a little bit of manipulation required, for example, in the Leontief equilibrium problem, but ultimately giving us this general form. And we've discussed how we can solve these problems exactly using elimination, approximately using projections and the idea of least squares, and how we can capture these ideas of elimination, least squares solutions in the LU decomposition for elimination and the QR decomposition for orthogonalization, which simplifies approximate solution with least squares. Both of these decompositions allow us to reduce the cost of solving linear systems of this form by giving us the opportunity to perform one perhaps expensive calculation, the act of going through forward elimination or the act of doing a Gram-Schmidt orthonormalization. But then once we've done that, we can solve for any number of right-hand sides with much, much reduced effort. So we do one expensive LU factorization, and then we can solve a pair of triangular systems very efficiently. We do one expensive QR decomposition, and we can solve a triangular system much more efficiently. Now, this is all fine for that type of system. We also, earlier in the class, introduced two other kinds of problems that also are linear systems, but have a different form. Markov processes and dynamical systems give rise to a different type of system of equations. They get expressed in this form: A times xi equals xi1, or xi plus 1. There's a concept of time, either explicitly or implicitly, that we're stepping through a sequence of events. And the values of at one particular point in time or one particular step in the process are used to dictate the values at the next step, the next point in time, and there's a linear relationship between those. In the context of Markov processes, these x are probability vectors. In the context of dynamical systems, they are more arbitrary vectors, but the general form is the same. Now we've seen that we can find stationary values to this, that is the set of vectors x that will not change over time, and that we can find these by setting xi and xi plus 1 equal to each other, and this gives rise to a homogeneous system that we can solve with elimination and so on. But this only lets us address the stationary case. What about the more general case? Solving this problem for a sequence of x's, right? This is a very common application in this problem. We're given a starting value x0, and we want to evaluate what the value of x is at point 1, 2, 3, 4, 100, 1,000, 1,000,000. As written, each of those steps involves a matrix multiplication, right? And when you're only doing 1 or 2 steps, that's not a big deal. But if you're applying hundreds of steps, hundreds of matrix multiplications, becomes quite costly. Is it possible to do something similar conceptually to the ideas of LU and QR decomposition? Can we find one expensive calculation that we can perform once on the matrix A, and after we've done that, be able to evaluate sequences of xi much more cheaply? Really what we want to avoid here is matrix multiplication by a large non-sparse, that is a matrix A that's not full of zeros, because that's the expensive case. We are going to begin our discussion of this thinking about a very, very special case, and this is going to motivate our discussion to a general solution to this problem. Think about the case where AX equals KX. That is, if there's an x where the effect of multiplying A gives us a scalar multiple of the original vector. This is, certainly if k was 1, this would be equivalent to the homogeneous case, or the stationary case, but we're not requiring this to be to k equals 1, just k to be anything. If we can write this, then xi plus 1 gets written as k times xi. We replace matrix multiplication with scalar multiplication. And if we take many steps, we replace the sequence of powers of n, subsequent multiplications of n, with powers of a scalar, which are easy to evaluate. So there is a case that would allow us to simplify the problem, but is this a case that arises? Is this a case that actually allows us to do anything meaningful for general problems? And that's what we're going to explore throughout the rest of this video. Let's begin with our definition. A definition of an eigenvalue and an eigenvector. We define, we think about a relationship here. If a scalar represented by lambda, the Greek letter lambda is the standard notation for an eigenvalue. We'll see what this means in a moment. If we can find a scalar lambda and a non-zero vector x that satisfy this equation, that is a times x equals lambda times x, the effect of multiplying x by the matrix A is simply to scale that vector. If we can find such a pair, then we say that lambda is an eigenvalue of A. And we say that x is an eigenvector associated with that eigenvalue. A couple important points. First of all, an eigenvector is always associated with an eigenvalue. Right? When we multiply an eigenvector by a, with a on the left, the result is a scalar multiple of that eigenvector, and the eigenvalue is that scaling factor. Right? So the eigenvector and the eigenvalue are linked in the sense that the eigenvalue represents what a does to that particular eigenvector. This is a definition. What use is it? Well, if we can express a vector as a linear combination of eigenvectors, right? So what do we mean by that? We mean that we can take some vector u and we can write it as some a1 times x1 plus a2 times x2 with as many eigenvectors as we may want, where each of these x1s and x2s is an eigenvector. What does it mean to be an eigenvector? It means that a times x1 is some lambda 1, some eigenvalue associated with that eigenvector times x1. And a times x2 is some lambda 2 times x2, and so on. And in this general form, lambda 1 will be different than lambda 2. These eigenvectors are different eigenvectors. They have different associated eigenvalues. If we can do this, then what would a times u be? Well, we can substitute this linear combination of u for u. A multiplied by this linear combination. We distribute the multiplication of a into this, and note that a1 and these small a1, small a2 are scalars, and so we can move them to the front. We have a1 times ax1 plus a2 times ax2, and so on. But x1, x2 are eigenvectors. That means we can replace this ax1 with lambda 1x1. We can replace ax2 with lambda 2x2. And here, lambda 1 and lambda 2 are just scalars. We have replaced the multiplication of a matrix by u with a sum of scalar multiplications. Much easier to evaluate this than to evaluate the product. If we think about replacing a here with a to the k, that is, having taken many subsequent multiplications of a, this similarly simply becomes a to the k times u, as becomes a1 times lambda 1 to the k times x1 plus a2 lambda 2 to the k x2, and so on. Even multiplication of powers of matrices become a sum of scalar multiplications, where we have to take the power of a scalar, but that is a much simpler thing to do than to take the power of a matrix. All right. So we've seen that a linear combination of eigenvectors would, if we were able to write a vector in such a form, would simplify the kind of matrix multiplication that we need to do in problems with dynamical systems, Markov chains, and so on. What else does the eigenvalue sort of eigenvector approach give us? Well, if we think about a to the k times u being this sum of linear combinations of lambdas raised to the k times their eigenvectors, when we multiply by large powers of k, or sorry, large powers of a, so a to the k, where k is a very big number. Right? What's going to happen? Well, if I've ordered these, this is a linear combination, so I can write the sum in any order I really want. Let's say I've chosen to write these in such a way that the first term has the biggest eigenvalue in an absolute value sense, and the second one has the next biggest eigenvalue, and the third one has the third largest eigenvalue, and so on. When we take powers of these eigenvalues, small differences get amplified. Right? This is what happens when you take powers. Right? If you think about the difference between 1 and a half, it's only a half. If you take 1 to the 1 squared, you keep as 1. Half squared becomes a quarter. The difference becomes bigger. 1 cubed is still 1. Half cubed is 1/8. You get a bigger and bigger difference. That doesn't only happen when you have a choice of 1. If we think about the difference between 2 and 4, it's only a difference of 2. When we square those, we get the difference between 16 and 4. Our difference becomes 12. Right? We increase the difference as we take powers. So even small differences in values of the magnitudes of individual eigenvalues become big differences. This single greater than sign means greater than. A double greater than symbol means much greater than. So we end up, when k is a lot bigger than 1, small differences become amplified, and that means that this first term becomes a lot more important than the other. If lambda 1 to the k is much, 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 much bigger than all of the other lambdas, then a to the k times u is dominated by this piece, and we can ignore most of the other terms with a small error. We can say that a to the k times u is approximately equal just the first term when k is much bigger than 1. K is, say, 100 or 1,000. This approximation becomes an equality in the limit. The limit as k goes to infinity, that is what happens if we take many, 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 many steps in a dynamical system or a Markov chain, is equal to the limit as k goes to infinity of this single leading term. Right? This gives us both a way to directly answer this question: what is this limit as k becomes very large, without having to just do multiplication many, 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 many times? We get a well-defined expression that can give us this limit. Note that this equality implies that this limit only is going to give us a well-defined finite answer if this expression can, and that's only going to work if none of the eigenvalues are greater than 1 in absolute value. If this greatest value is 1, then the limit as k goes to the infinity is still lambda 1 to the k will be 1, and will give us this a1 times x1. If the lambda 1 is actually less than 0, this will all go to 0. If lambda 1 is greater than 1, then this expression has to blow up, some of the values have to become larger and larger and larger, no matter as we increase k. All right. So we've seen two potential uses of these eigenvalues and eigenvectors. One that can simplify the calculation of a times u, or a to the k times u, and that we can use this idea to also give us limiting behavior of what happens as k goes very large in a to the k times u. So there's a utility to eigenvalues, but there's still some important open questions. One of the biggest ones of these is the first. can we always write a vector as a linear combination of eigenvectors? If we can do some interesting things, but is it possible to do so? In order to answer this question, we need to answer a few sub-problems, if you will. Do all matrices have eigenvalues and eigenvectors? If a matrix does have eigenvalues and eigenvectors, how many of them are there? How many eigenvalues does a matrix have? How many eigenvectors does a matrix have? This is a counting question that would allow us to address, can we theoretically write a vector as a linear combination? In order to do this practically, we need to know how to actually find eigenvalues and eigenvectors. And that's what we're going to explore in the next part of this video. First of all, let's focus on finding eigenvalues. Now remember, how have we defined an eigenvalue? An eigenvalue is a scalar lambda that can be associated with a non-zero vector x that satisfies this equation, ax equals lambda x. Let's rearrange this in the same way that we did when we were trying to find stationary solutions. Right? We move the lambda, ax over to one side, so we now have lambda x minus ax equals 0. This is a scalar times x and a matrix times x. We can't factor it directly, but if we multiply lambda by I, then we can factor this out and give a general expression here as long as a is square. Right? Actually, we know already that a must be square if we think a little bit about what this expression requires. If X is an n by 1 matrix, and this is a scalar multiple, the right-hand side has to be an n by 1. How do we get an n by 1 matrix with matrix multiplication? Well, the inner dimensions have to match. We have to have an n here, and the final result has to be of the right shape, so A has to be an n by n square matrix. This actually starts to address one of our questions. Only square matrices can have eigenvalues. Non-square matrices cannot satisfy this eigenvalue equation. Now, if we have a square matrix, we can now address this question of whether there's eigenvalues and what they might be. Let's look at this. We have a matrix, lambda I minus a times x equals 0. Fundamentally, this is really just a expression of the form m times x equals 0, where m is lambda I minus a, just a matrix. And what is this? This is a homogeneous system of equations with a square coefficient matrix. If m is non-singular, then this system has a unique solution of only the 0 vector. So if this M matrix, lambda I minus a, is non-singular, there is no non-zero vector that satisfies this. The only way we can have a non-zero vector that satisfies this equation is if M is singular. If M is singular, then this will have many solutions along a line, on a plane, or so on. This gives us a criterion for evaluating whether something can be an eigenvector. Lambda is an eigenvector or eigenvalue of A if and only if this matrix, lambda I minus A, is singular. It's non-singular. This system only has the zero vector as a solution. How do we determine whether a matrix is singular or not? Well, we can do elimination, but elimination with a symbolic variable like lambda often becomes messy. It's easier to write this in the form of the determinant. If the determinant of lambda I minus A is equal to 0, then lambda is an eigenvalue. This is going to give us our approach to find eigenvalues. This determinant is going to end up being a polynomial of degree n in lambda. Lambda is going to be a variable of this polynomial. A polynomial of degree n has at most n roots. What do we mean by that? Polynomial of degree 1 is a straight line. A straight line can cross the origin only at most one time. A polynomial of degree 2 is a parabola. A parabola can equal 0 or cross the x-axis at most 2 times. A polynomial of degree 3 can cross the x equals 0 line at most 3 times, and so on. Right? This means that an n by n matrix can have no more than n eigenvalues, starting to give us some insight into how many eigenvalues a matrix can have. I think probably the best way to sort of get a better feel for how we use this determinant, this characteristic polynomial, is by going through some examples. So let's do that. What are the eigenvalues of this matrix, this 2 by 2 matrix that happens to be square and happens to be symmetric? The first thing that we do is we want to evaluate this characteristic polynomial. Right? This will give us lambda times I. Lambda times I will be lambda, lambda, 0, 0. This is lambda I minus A minus 1, 1, 2, 2 will give us lambda minus 1, negative 2, negative 2, and lambda minus 1. This is a 2 by 2 determinant. We calculate this by multiplying the diagonal entries, lambda minus 1 squared, minus multiplying the off diagonals. Negative 2 squared is 4. And then we expand. Lambda minus 1 squared is lambda squared minus 2 lambda plus 1 minus 4. Group these two terms together into a negative 3. And this gives us, as we mentioned, a polynomial. This was a 2 by 2 matrix. It gives us a polynomial of degree 2 in lambda. We start with a lambda squared, lambda term, and a constant term. What we want is to find values of this polynomial that equals 0. We want to solve for the characteristic polynomial being equal to 0, the roots of this polynomial. One way to do this is with factoring. Recall that how we factor a polynomial, a quadratic, is we look for a pair of numbers that multiply to give us the last number, a times b equals negative 3, and add together to give us the middle number, a plus b equals negative 2, and this is satisfied by a equals negative 3 and b equals plus 1. We can do this and then factor this into lambda minus 3, lambda plus 1. So the roots of this characteristic polynomial are found when this factored product equals 0. This can equal 0 if either lambda minus 3 is 0, which means lambda is 3, or if lambda plus 1 is 0, lambda equals -1. This gives us 2 eigenvalues for this matrix. Let's go through another example. What are the eigenvalues of this matrix? This is now not a symmetric matrix. Let's try this one. Right? And it doesn't have equal values on the diagonal either. Let's take a look at how we do this. Again, lambda I minus a. We have lambda minus 0, 0 minus 1, 0 minus -1 is +1, and lambda minus 2. We find the determinant by multiplying the diagonal entries, lambda times lambda minus 2, minus the product of the off-diagonal entries, minus -1, and expand this. Lambda times lambda minus 2 is lambda squared minus 2 lambda. Negative of -1 is +1. And this, again, actually is directly the form of a minus 1 squared. -1 squared gives us +1. -1 plus -1 gives us -2. This factorization. So the determinant of this expression, the characteristic polynomial, will be equal to 0 when this term is 0. This can only happen when lambda equals 1. In this case, we get 1 eigenvalue. In the previous case, we had a 2 by 2 matrix that gave us 2 eigenvalues. Here we have a 2 by 2 matrix that gave us 1 eigenvalue. Let's do another example. This is going to be one where we can't factor easily. This happens to actually be a skew symmetric matrix. Form our matrix to evaluate the determinant, lambda minus 1, 0 minus -2, 0 minus 2, 0 minus -2 is +2, and lambda minus 1. Evaluate the determinant, multiplying off the diagonal terms, lambda minus 1 squared. Subtract the product of the off-diagonal terms. 2 times -2 is -4. Expand this product, lambda squared minus 2 lambda plus 1, minus -4 is +4, gives us lambda squared minus 2 lambda plus 5. We try to do that factoring trick. We want something a times b equals 5, but a plus b equals -2. There is no easy way to do that. Right? The only integer products that give us 5 are a equals 1, b equals 5, or vice versa, or them both being negative. And neither of those can give us -2 as a sum. So instead, we resort to using the quadratic formula. With 2 by 2 matrices, we can always use the quadratic formula to help us find eigenvalues. So we want our determinant of this characteristic polynomial, a quadratic in lambda, to equal 0. We simply plug these values into the quadratic formula. In ax squared plus bx plus c, we have an a of 1, a b of -2, and a c of 5. So this gives us negative -2 is 2, plus or minus 2 squared is 4, minus 4 times 1 times 5 is 20, divided by 2 times 1 is 2. Right? Now, when we look at the discriminant, the value inside this root, it's -16. Right? We can't find a real number whose square is a negative number. But this doesn't mean that we have to completely stop. We can actually find imaginary numbers that will solve this problem. Remember that the imaginary number, is the square root of -1. It is defined as this sort of value. A number that if we multiply it together would give us -1. And so the square root of -16 is the square root of 16 times the square root of -1, or is 4 times I. Right? When we plug that 4I into here and divide through by 2, we get lambda equals 1 plus or minus 2I. We get answers. We get 2 eigenvalues, but they are imaginary numbers. This is not uncommon in finding eigenvalues. Complex numbers, imaginary numbers arise. It's important to know that this happens. It's not fundamentally a problem in using eigenvalue decomposition. I am not going to expect you to be working extensively with complex eigenvalues. Right? I think we have enough on our plate dealing with the simpler cases, but it's important to know that this can happen. Right? So with these examples, let's sort of highlight some of the things we've learned for the 2x2 case, and I'll let you know that these extrapolate to higher dimensions. And we'll play around with some of these in worked examples later. For an n by n matrix, this characteristic polynomial is a polynomial of degree n, which can have at most n roots, but some of these, so for example, we can have, our characteristic polynomial degree 2 gives us 2 roots, but some of them may be repeated, sometimes called degenerate. What does that mean? It means when we factor them, we actually get the same factor multiple times, and that leads to having less than n roots. Some of the roots might be imaginary or complex numbers. So here we get 2 complex roots, but we don't get any real roots. This lets us come to some final conclusions about the number of eigenvalues a matrix can have. An n by n matrix can have at most n distinct eigenvalues, never more. Every n by n matrix has at least one eigenvalue, like shown here, but they may be complex. Right? It is possible for a matrix to have no real eigenvalues and only to have complex eigenvalues. All right. What about eigenvectors? Right? Let's go back to our original expression. If lambda is an eigenvalue, then this matrix is singular. Its determinant is 0. What does this mean? It means there must be a non-zero x that satisfies our starting expression. This is represented by rearranging this in the form that we've seen before, giving this matrix that we, for eigenvalues, use to derive the characteristic polynomial. But what is this? This expression, right, we just saw in our previous, one of the previous slides. This is really just mx0, so mx equals 0 with m equals lambda I minus a. It's a homogeneous system. We're looking for non-zero solutions to a homogeneous system. The solutions of a homogeneous system are the null space of that matrix. Every vector in the null space of this lambda I minus a is an eigenvector of A with corresponding eigenvalue of lambda. This tells us right away that if lambda is an eigenvalue, it has many eigenvectors. It has every vector in the null space of this matrix being an eigenvector. So perhaps we can discuss an eigenspace, a vector space of eigenvectors for this eigenvalue. Right? Now, although a homogeneous system with a singular coefficient matrix has many answers, an infinite number of answers, that doesn't mean that everything is an answer. We describe the null space with a basis. We can reduce down to a linearly independent number of a number of linearly independent solutions. That gives us a basis for the vector space. And as long as we have a basis, we have everything we need to generate any of the solutions. And so we might look for a basis for this eigenspace. How do we do this? How do we find linearly independent eigenvectors for this eigenvalue? Nothing new. All we're trying to do is to find a basis for the null space of a matrix. Such a basis is given by the special solutions to the homogeneous system. The basis for this eigenspace associated with lambda, that is a set of linearly independent eigenvectors associated with this lambda, are given by the special solutions to this homogeneous system, using exactly the same approach that we've explored for more general matrices. All right, so let's think about this. Sorry, this is essentially the same slide, duplicated for some reason. One important point that is added on this one: each distinct lambda has a distinct eigenspace, and this is important to sort of note. We generally are trying to find a basis for each of the eigenspaces. Of course, if we have a different lambda here, this matrix will be different. If this matrix is different, its null space will be different. Right? And so it's not a matter of finding just an eigenvector for an eigenvalue. It's a matter of finding eigenvectors for each of the eigenvalues. Let's go through a couple more examples to highlight what we mean by this. Let's start by finding a basis for the eigenspaces of this matrix. This is the one that we worked with before, the first example for eigenvalues, and we had seen that it has two eigenvalues of lambda equals 3 and lambda equals -1. To find bases, linearly independent eigenvectors for these eigenvalues, what do? We set lambda equals 3 and compute this matrix. Lambda I minus A is 3 minus 1 is 2, 0 minus 2 is -2, 0 minus 2 is -2, 3 minus 1 is 2. So this is our matrix that we start with. We go through elimination. Pivot, eliminate downwards. Second row is actually a scalar multiple of the first, so it disappears. Then we scale with the first pivot to give us our reduced row echelon form with a 1 in our single pivot position. We have one pivot, one free variable. The free variable is given by is the second value, x equals 2. We set x2 equals 1, and then we read off the pivot value by negating the entry in the free variable column to give us a special solution of 1, 1. This 1, 1 is a basis for the eigenspace associated with this first eigenvalue of 3. We then can do the same thing for lambda equals -1. We set lambda equals -1. Lambda I minus A is -1, -1, 0, 0, minus 1, 1, 2, 2. -1 minus 1 is -2. 0 minus 2 is -2. 0 minus 2 is -2. -1 minus 1 is -2. Again, the second row is a scalar multiple of the first, actually identical to the first, so it disappears, it zeroes out in the first round of elimination. Scale our second row, giving us this reduced row echelon form. Once again, we have one pivot and one free variable. We set the free variable equal to 1 and find the value for the pivot column by negating the entry found in the pivot column, or in the free variable column. So we get a -1, 1 as our special solution. -1, 1 is a basis for the eigenspace associated with this other eigenvalue. Here we had two independent, distinct eigenvalues. We got bases for each of them. These are linearly independent vectors in R2. Actually, they turn out to be orthogonal even. Two linearly independent vectors in R2 span all of R2. For this matrix, we can represent any vector in R2 as a linear combination of eigenvectors. The second matrix we worked through as an example was this one, and it gave a single eigenvalue of 1. It was duplicated, if you will, in the factorization. We apply exactly the same approach, but we only have to do it for the one single eigenvalue. We set the eigenvalue equal to 1. This is lambda I is, of course, just I if lambda is 1. I minus 0, 1, -1, 2 is 1 minus 0. 0 minus 1 is -1. 0 minus -1 is +1. And 1 minus 2 is -1. Identical rows. The second one zeroes out in the first round of elimination. Because we actually had a starting entry of 1, we don't have to do any scaling. We're already in reduced row echelon form. And so we can pull out our special solution of 1, 1. Right? This actually gave us the same matrix that we had for lambda equals 3. So we end up with the same eigenvector for this different matrix. 1, 1. Now there's only one free variable. Right? That means that the dimension of the null space of lambda I minus A is 1. Right? One free variable, a one-dimensional null space. The set of solutions lies on a line. We have a basis of one vector. This is the only eigenvalue. That means we can't find any other eigenvectors. The only eigenvectors for this matrix are linear combinations of this one, scalar multiples of this single vector. Since the eigenspace is has dimension 1, not dimension 2. It does not span the whole space of R2. For this matrix, we would not be able to write any vector in R2 as a linear combination of eigenvalues. We could only do that for vectors that happen to sit on this line. Let's take a look at the complex case just to show you that this can be done. The last example we had, this matrix gave us complex eigenvalues, a pair of them, 1 plus or minus 2 times I. We can do exactly the same thing. we can plug this value in. And what happens when we do that? Lambda times I becomes 1 plus 2i. 0, 0, 1 plus 2i. Subtract a. 1, 1, 2 minus 2. 1 plus 2i minus 1 just becomes 2i. 0 minus 2, negative 2. 0 minus negative 2 becomes plus 2. And 1 plus 2i minus 1 becomes 2i. We can do elimination on this, but it's a little bit trickier. I'll just kind of walk you through the idea of doing this. Right? If we multiply this first row by I, that would give us I squared and I. But I squared is just negative 1. So that gives us negative 2, negative 2i. We can add these two rows together to eliminate our first pivot. Negative 2 plus 2 is 0. We're adding them together, negative 2i and 2i. What we actually see, these two rows are scalar multiples of each other. They just have an imaginary scalar multiple. That means we have a 0 row. We need to scale this single pivot. We can do this first of all by multiplying by I. This gives us, again, I squared and negative 2i. But I squared is negative 2, so this would give us a negative 2, negative 2i, 0, 0. Then we divide this first row by negative 2, or multiply by negative half, and this would give us 1 and I. We're in a reduced row echelon form. We actually can use the same rule. We have a single free variable, x2 equals 1, and we pull out the pivot entry by negating this value here. It was an imaginary number, so we end up with a negative I here. Right? The only difference between these two is a sign of the imaginary piece. These two answers are actually what we call complex conjugates. The complex conjugate of a complex number, if C is A plus I times B, the complex conjugate, which we often denote with a star, is A minus I times B, which is exactly what we have here. This is actually a general result. Complex eigenvalues for matrices that have real numbers always are in complex conjugate pairs, for reasons we're not going to dig into. But what that also means is that when we actually go through this process, the only thing that has really happened is that there's a sign difference for these diagonal entries. The diagonal entries became negative 2i instead of plus 2i. Everything else actually works out exactly the same, that these end up being scalar multiples. We do the scaling and we end up with a 1 minus I here. When we end up with this in form, we find our solution exactly the same way. We set our free variable. Pivot was in the first column, free variable is the second, set that equal to 1, and then negate the appropriate entry to get our pivot value of I. One-dimensional basis for each of these. We have a basis for the eigenspace associated with our first eigenvalue, a basis for the eigenspace associated with the second. One important result here, when we have complex eigenvalues, we get complex eigenvectors. These are linearly independent. They actually also turn out still to be orthogonal with the right definition of orthogonality in complex vectors is a little bit trickier. We're not going to get into that. The point here is really to demonstrate that we can do this. The fact that we get complex eigenvalues doesn't fundamentally limit our ability to move forward. We actually, in this case, end up with two linearly independent vectors. We can generate any vector as linear combinations of these, with the caveat that we are now dealing with complex numbers, which means the scalars we multiply by in linear combinations might be complex. There's various ways that we can pull apart the real and the imaginary piece of matrices like this, and for advanced work in linear algebra and advanced applications of eigenvectors and eigenvalues, this is something that we do. However, in this class, we are not going to go there. This is really the limit of our discussion of the complex case. All right. In summary, what have we seen? We've seen that every square matrix has to have at least one eigenvalue and one linearly independent eigenvector. An n by n matrix has at most n eigenvalues and at most n linearly independent eigenvectors. But various possibilities in between these two bounds can exist. We can have fewer than n eigenvalues. We can have fewer than n linearly independent eigenvectors. How do we find these? We find the eigenvalues by asking for the solutions to the determinant of lambda I minus a equals 0. This gives us a polynomial in lambda that we solve for the roots of. Those roots are the eigenvalues. Once we have the eigenvalues, the null space of this matrix that now has a number for lambda rather than lambda being a variable, the null space of this matrix is the eigenspace associated with this, and we describe that, we characterize it by finding a basis, the special solutions of this piece. We don't really need any more new tools to do this. We've already discussed the determinant and how to compute it. That lets us determine what this characteristic polynomial is. We've had practice and discussed on finding bases for homogeneous, for null spaces by special solutions. There's nothing new there. We just do all of this on this special form. In an accompanying worked example videos, we'll go through more examples of finding eigenvalues and eigenvectors of matrices, including 3 by 3 matrices and larger matrices of special forms where the arithmetic doesn't get too messy. And in a subsequent content video, we're going to expand on these basic ideas of defining eigenvalues, eigenvectors, and how to compute them to derive what we call the eigenvalue decomposition, an analogous matrix factorization or matrix decomposition that we can use to simplify solving problems. Thank you, and goodbye.